So today we're going to continue with being able to simplify radical expressions by using either multiplication or addition and subtraction. So last class period we did multiplication on pages 1 and 2 of this packet. Today we're going to do addition and subtraction, which uses some similar properties to how we add and subtract polynomials, but we're dealing with radical expressions. So this is page 3 starting on your packet, and it's going to be pages 3 and 4, and then the work to do after that is on Canvas. But the concept of adding two expressions together in terms of this question here, what are like terms? When we added polynomials together, we saw that 2x plus 3x was just 5x. They are like terms. 2x squared plus 3x squared is 5x squared. Once again, they are like terms. 2xy plus 3xy are also like terms, and our answer is 5xy. In order to add expressions together, whether it be polynomial expressions or radical expressions that have the root, we need to have those like terms. So look at these three examples and try to generalize how would you put into words a statement of like terms have this. And one of the biggest things that you need to kind of understand and maybe see from these examples is that like terms have the same variables, same exponents, but do not need the same coefficients. But do not need the same coefficients. Because when you're adding like terms together, all you do is add up the coefficients. There are 2 of these x's, 3 of these x's. There are now 5 of these x's, right? So that's kind of the idea. They have to have the same variable, but they also have to have the same exponents. And in order to then go to the next step, they don't need the same coefficients. That's fine. We just add up the like coefficients. So in terms of dealing with exponents, our unit here, in terms of radicals, radicals are fractional exponents, right? The square root of x and x to the 1/2, those are like terms, even though they look different. So you would be able to say that, yes, these two are like terms. And then if you were to add them, it would probably be easiest just to call it, both of them the square root of x and maybe add them. There's one of these, one of these. There are 2 of these, right? And notice how I didn't change the square root. I didn't change the x. Here, x and y, it's still an x and a y. X squared, still an x squared. X and an x, still an x. Leave the variables alone, leave the exponents alone, just add or subtract the coefficients. And what we're going to see before we get to the kind of grouping and then a couple examples to finish up this video is when we're dealing with these like terms, there is something different about radicals than just polynomials. These 3 are polynomials. What I have right here is a radical expression. Now, radicals not only need the same variables, not only need the same exponents, but when you think about exponents, those are roots, right? Square roots, cube roots. So they got to have the same root on it, right? So square roots compared to cube roots. I can't add up a square root with a cube root because technically they do not have the same exponent. An exponent of a 1/2 compared to an exponent of 1/3. So this is just asking you to group them in different ways based on what you see for like terms. So the ones that just have an x have squares. So we got this one here, this one here as well. Oh, that's looking kind of like our trapezoid. Let's see here. Just an x, just an x, just an x. That's all I see. The next one, square root of x. Let's do triangles for that one, for the square root of x, or x to the 1/2. These are all the same. X to the 1/2, or square root of x, square root of x. One more here. Okay, what's our next shape? All right, circles. We could do to the 1/5 as circles. 1/5, 1/5. Okay, 1/5, all like terms. And that's it. We can do our next shape here. Got a little cloud going on. A cubic. 2x to the 3rd. X to the 3rd is different than cube root, right? X to the 3rd. And that's it for there. And then our last two, let's see here. Cube root of x squared. Think about that as a fractional form. That is x to the 2/3. So any of these x to the 2/3, I'm going to group up like this. X to the 2/3. X to the 2/3, or cube root of x squared. Notice those are like terms because same variable, same exponent on the x, and also same exponent for the root right there, right? Not really exponent, the root. And then the last one, cube root of x. Cube root of x. And I think that's all of them. So once we see those like terms, we can add them up. So here's what we got to look at. When adding and subtracting radicals, you have to have that same root. The root is actually the exponent, right? Same radicand. Just a quick definition. If you have something like this, and this is like some number, this is called the nth root. This is the radical sign, like it's just the symbol for the radical. And then what's on the inside is called the radicand. So it's basically saying they have to have identical insides. They have to be identical. Same variables, same exponents. It's got to all be the same in order to add up those like terms. So let's look at what we have here. And it does have one other note. You may want to simplify first. What I mean by simplify first is like taking things out. You know, if you can square root a square, maybe take that out to the outside, and you might see things actually turn out to be like terms. So let's see here. 2 of these cube root x squareds plus 7 of these cube root x squareds, well, those are like terms. Cube root, x, x, square, square. 2 of them, 7 of them, 9 of them. And that's it. Why? Because I cannot simplify further. Right? I can't take anything out of the variable, so we're good. Okay, next one, cube root x squared y, cube root x squared y. 3 of them minus, technically, remember, just deal with the coefficients. 3 of them minus 1 of them. There are 2 of these. Okay, move on. Number 5, I've got 3xyz, 4th root xy. 2xyz, 4th root xy. Same variables in front, same variables in front. Root xy, xy, 3 of them, 2 of them, 5 of them. I don't mess with the exponents, don't change them. Leave everything you have for those like terms. All you're doing is adding the coefficients. Let's look at the next one. xyz, 4th root xyz. xyz, 4th root xy. There's no simplifying of the roots. I can't take anything out, and also I notice they're not the same. Guess what? We're done. You can't do anything. That's going to happen sometimes where there's no like terms in a problem. You have added everything you possibly can. In the same way that sometimes when you have like 3x squared plus 5x, you can't add them. Like that would just be your answer because they're different terms. They're not like terms. Okay? Just a couple more here real quick. Cube root x squared y, cube root x squared y. 7 of them, technically 1 of them, 8 of them. So not too bad so far. Let's look at what we have next here. X squared y, 64, yikes. Z to the 5th, z squared, 25. Okay, there's a lot going on, and they are not the same. Okay, so that's the first thing that stands out to me. I know they're not the same, but there might be something we can do. These are square roots, and then I've got like higher exponents on the inside here, square roots with some higher exponents. So I can actually use our properties of the square root of x squared simplifies down to x. In the same way, the square root of x to the 4th is x squared. I could use those properties to like take something out, and they might actually be equivalent. I honestly don't remember. We'll see what happens. So if I were to square root this 64, okay, that's going to be an 8. I'm going to take an 8 out. This x squared and the y, they're just going to hang out. But then I need to square root a z to the 5th. This is the type of stuff we start doing mentally. We think about a square root into a z to the 5th. I need a whole bunch of z squares. How many z squares are there in a z to the 5th? there are two sets of that with one left over. So what could you do? You could take out a z squared, and a z is going to stay on the inside. So there's going to be a z squared out here with a z on the inside. And just to show the expanded form, z squared, 2, 4. There's the fifth one. This comes out, giving us that right there. Okay? Be clear with that break apart. Plus, z squared is going to stay there, but square root of 25 is 5. Square root of x to the fourth is x squared, and square root of y squared is y. And that z, it's just going to stay on the inside. Now let's look at what we have here. X squared, yz squared. X squared, yz squared. Square root z, they're identical. We've got like terms. We are all set and ready to go. Leave this exactly as you see it. All you have to do is add up your coefficients. 8 of them, 5 of them, 13 of these right here. And we've got our answer. Okay, so most difficult one so far by far, but we're just trying to break it apart, see if they are like terms. It's kind of disguised in a way to show that they are like terms. Okay, let's see here. Fifth root x cubed y, cube root, that's different. That's not good. In terms of adding together, can't do it. Fifth root, cube root, x cubed y, xy, fifth root x cubed y. These two right here can be combined, but it cannot be combined with the middle one. They're not the same. So let's reread this and say, okay, I've got 4 of these minus 9 of these. I have negative 5 of these. Don't change the exponents. Minus 2 cube root x, y. And let's see, 5, 3, they're different. I can't take anything out. We know we are done at this point. Last one for the day. We need to square root something, but look at these numbers, not working out that well. Let's see here. I'm going to fully expand this one to try to show the relationship because they are not the same now, but I think they're going to be. Okay, let's see. X squared y, the number 8. The number 8 can be broken apart to two numbers where one of them is square rootable and the other one is not. 4 and 2. I'm just going to call it 4 times 2. Then z to the fifth, we did this actually above. This was z squared, z. Now you don't have to do this expansion every time. I'm just trying to show like all steps to it to show how to get to that next line. And notice they are like terms. But then the next part has a z squared out in front. And then we're left with 50. Well, 50 is not square rootable as is. It's a decimal. But I do know two numbers that multiply to be 50, one of them being square rootable. So I'm going to call that 25 times 2. X to the fourth is x squared times another x squared. Remember, I'm doing squares because it's a square root. I'd be doing groups of cubes if it's a cube root. Y squared and a z. Let's take out everything that we possibly can and see what we're actually left with. I can square root the 4 to bring a 2 out. Square root of 2 stays inside. I can take a z out. I can take another z out, but there's a z left on the inside. So we've got that. Okay, let's do the next one. I can take the square root of 25 is 5. Square root of 2 stays inside. I can take an x out. I can also take another x out. I can also take a y out. So x squared y, that z squared is still hanging along for the ride. And then I cannot square root the 2 or the z, so it stays in. All right, let's see here. X squared, yz squared. X squared, yz squared. 2z, 2z. Just as a quick side note, if this 2 wasn't here and this one was, can't add them. They have to be the identical radicand. Remember it said that above on one of the first lines here? The radicand is the inside. The inside has to be completely identical, even with the coefficients. Okay, even with the coefficients on the radicand. Let's see here. Sorry, just going back one step. I'm gonna get rid of the arrow I had drawn there. Okay, so 2 of them. 5 of them, 7 of these right here, and that's your answer. Disguised like terms. They didn't look like terms initially, but they actually are. All right, that's it for today, guys. Homework assignment, you guys can see it on Canvas. But once again, the main goal was trying to understand what are like terms, how do you add them or subtract them, and relating not just polynomial like terms in terms of addition subtraction, but also radical terms. So understanding radicals are fractional exponents, so it follows the same properties. Um, and then also sometimes they're disguised. So you could simplify first, like take something out, and it's like, oh, I actually have the same exact terms on both sides. I can just add up the coefficients. Okay, that's it for today.